Good morning, everyone. Thank you so much for coming to my presentation here. I feel very honored to be first time in Indonesia. It's very nice to be here, to be welcomed by our partners, and of course have a chance to tell you a few things more technically in nature about testing measurement for partial discharge. As you know, partial discharge, it's a very interesting topic for many, and it became more prominent lately when people realized that this technology can be used to do actually, predeterminations of the quality of insulation. I'm just curious in this hall, how many people are familiar with the concept of partial discharge? Just maybe by hands. How many people have worked or have anything in conjunction with partial discharge? Okay, this is rather important for me because then I will tell you things in such a way that hopefully by the end of this conversation you will know much more and you will have a chance to maybe those, let's say, student days. I was also once a professor, so the net result here is I hope that my delivery will be in such a way done that you will feel comfortable with the subject and not threatened by it. So I prepared a bit of an agenda, and I wanted to show you, of course, using different devices that we have created in our company, how partial discharge is being tested for, is being measured, is being monitored, and of course, I will start with the very beginning. Maybe I should mention the fact that our company invented the so-called phased resolve partial discharge diagram. So, because maybe some of you don't know exactly what partial discharge is probably a good idea for me to mention that when you have an insulator, and when this insulator is subjected to an electrical field, the chances are that certain electrons are going to move through this insulator. Of course, when they find a void, when they find a part of the insulator that is not offering the same electrical strength, then they are going to move faster. They are going to more or less jump, right? So there will be a charge, a number of electrons that are going to move from one region of this insulator to another region. Well, very interesting. When they do that, when they move from one region to another, what they do, they create in time domain an impulse. So this impulse, of course, the rise time of this impulse depends very much on, how it's the medium in which these electrons are performing the jump. If it's compressed SF6, the impulse is very sharp. In air, maybe less. In other materials, it depends. So when you have always an impulse like that, from an electromagnetic point of view, most likely you're going to create UHF radio waves. Equally, when you have an impulse like that, if it's very big, you may even hear it because there will be things happening, wave pressure, acoustic wave pressure, that can be heard, measured. Sometimes such kind of impulses and the movement of electrons will even be seen. So, for instance, you can look in certain frequency spectrum and practically see discharges, and that's how that beautiful photography with those trees that you see is being made. And very interestingly, when you have such an impulse, right, this has a certain magnitude. And this magnitude, of course, corresponds to the number of electrons that have moved, have jumped, okay? And usually the charge, so in other words, the number of electrons that jump are measured in Coulomb. Of course, Coulomb is a very big unit, so people are talking about picocoulomb, nanocoulomb. So in other words, same as they speak about microfarad and nanofarad rather than farad for capacitance. So these coulombs, or picocoulombs, or nanocoulombs, are referring to number of electrons, the magnitude of the charge that has been created. Now, as you probably know, if you divide the charge over time, you get to amps, okay, just to connect things, the units, and so on. So, when you have this charge, this impulse that I mentioned to you, ultimately a device can basically pinpoint where this impulse, where this transfer of electrons happened in phase, and in phase of what? In relationship to the phase of the AC voltage. So what you see on this diagram here, I don't know if this is going to be, I will show you. So what you see on this diagram, you can see the voltage that goes through its normal cycles, 50, 60 hertz, depends on the country, depends on the region. And then what you see equally on this diagram is a projection. One of these points here represents the fact that somewhere at this exact moment in phase, there was a charge of this magnitude. So there was an impulse that went up, and then it put this point over here. Now, when you have more charges, because of course time goes by, and you have the voltage oscillating exactly the way I described, then there are charges that they are occurring with the same magnitude in the same place. So what's happening then, in the case of this diagram gets colored deeper and deeper. You see these reds, means that lots of charges happened exactly at this phase with this negative magnitude. And you can see also on this diagram, it's very interesting that you have a positive part of the diagram and a negative part of the diagram. Okay? So, yes. It's very interesting also to realize that these diagrams are basically offering a signature of the problem that somebody may see inside of the isolation material. This particular diagram that you see here has been a diagram acquired from a rotating machine, from a generator. These generators, as you probably remember, they are basically copper bars. The copper bars are surrounded by mica tape. Then many copper bars end up being surrounded by more mica tape, and eventually you create the stator bar. And the stator bar is basically creating eventually the stator of that big generator that can be as big as this room. Okay? So now, in the case of a rotating machine, in the case of a generator, what's happening is that you will have the situation by which means there are small voids inside of this wind mica tape. And those voids will give this kind of pattern that you see here. These are voids. Then also at the end of the stator you have discharges. So you can see discharges, things that happen on the positive side of the cycle have a certain meaning. Things that happen on the negative side of the cycle have another meaning. So what I'm trying to convey to you is that for each insulator, being that what's happening inside of a transformer, being that what's happening inside of a GIS, being that what's happening for a rotating machine, being that what's happening for a cable, all these assets, when they have insulation problems, they do experience actually partial discharge, and for each type asset, there is a signature. So this is some takeaway for all of you, that when a certain voltage is being applied, let's say more than 1,000 volts, all insulation materials will experience partial discharge if they are not perfect, and most are not. And then for each fault inside of this insulation material, there is naturally a signature. So that's the takeaway message. We invented this diagram, and as a result of our research work, we were able to devise several things. We were able to devise both test and measurement devices that are capable of acquiring this diagram. And equally, we were able to connect the dots with the real problems that various insulation materials have. Here, I just showed in this agenda a number of measurements. These measurements are being done together with, yes, our devices, but honestly can be done with any device that actually is of good quality and can be used for partial discharge determinations. Our company is just a pioneer in this direction. So So I'm going to show you, for instance, and of course you will have access to this presentation, that in particular a system that I'll demonstrate now has a number of applications, and I listed them here because it's very important to know for you that for different type of assets, from transformers to rotating machines, for cables or R&D, there are different norms, different standards that apply. So the world has worked before, and with our participation, several of our fathers in our company, like Professor and Dr. Detlef Gross, we acquired enough information to help all these people to establish a standard. So we were part of IEC, we were part of, and we are part of IEC, part of IEEE, part of MEGGER, and as a result we created both standards and guidelines. So you should be aware of those, because when you have assets in your jurisdiction, you should be aware that they need to be either tested or there are certain norms that need to be respected. And MEGGER, for instance, will give you guidelines how to test certain things, and I'm trying to show you how our systems are being used to actually do such kind of tests. And here I also listed for each device, so that you know the type of users are being summoned to actually employ such devices in their day-to-day activities. And so this table can leave you with a lot of information that effectively will help you select both the standard and the type of people you need to talk to. Here I'm going to show you, for instance, what's happening inside of any big power transformer factory. You won't believe it, but many, many factories around the world, for instance, former colleagues from ABB, now Hitachi, about 56 plants in the world are using precisely this system that is pictured here. To do what? To do partial discharge testing based on a standard called IEC 60270. So this standard specifies the levels and effectively, ultimately, the patterns that are acceptable when a transformer is being produced, when a transformer is being effectively delivered to an end customer. So if you are part of a power utility, normally you should always ask for these particular tests, because they are very revealing towards or versus the asset that you're about to put in action. So normally here, if you look, you will see the bushing. At the base of a bushing, there is a capacitive coupler here that is being used to measure tan delta, but equally it's used for determining partial discharge. So these bushings here will have such a capacitive coupler, and with the help of a quadrupole, this capacitive coupler will offer you or us, to a system like this ICM system, the information about what's happening with partial discharge. Okay? Now, of course, in order to understand and compare from one transformer to another, from one bushing to another, information about partial discharge, it's very important to calibrate the measurements. So in other words, to issue, let's say, a known quantity of picocoulombs at the top of the bushing and effectively calibrate the measurement system to that value. So for instance, our company produces these calibrators, moreover has a specialized DAX lab that we calibrate calibrators both for us and our competition. That's why they receive a special mark. It's the only lab that exists in Europe, in Germany, and of course we are using it in order to also calibrate our calibrators. So once the entire measurement channel has been calibrated, you will be able to do what it's called in the transformer business inside of the factory, the applied and induced voltage tests. How many of you are familiar with applied and induced voltage tests for power transformers? Okay, so I will explain a bit also that. So when you have a power transformer, from the low voltage side, you are going to induce into that transformer a certain voltage and make a record of partial discharge. When for instance, you would like to know how this transformer behaves from the high voltage side, you're going to apply to all phases simultaneously a high voltage. So we have such kind of test containers that we can do that, but the factories do have that implemented, and they will either induce or apply. And during that time, they will test for partial discharge. What does that tell anybody? It will tell you about the quality of that particular transformer. So without looking at the values of partial discharge when you produce a transformer, without looking at the patterns, you will never know what kind of test object you got. So it's a very important test. It's a very important standard, this IEC 60270, and it's very important for all of you power utility people that they are commercializing such transformers, to ask for those test reports. Equally, when you have a distribution transformer, the same norms apply. The same quality needs to be required from the manufacturer. And you should get these test reports, the partial discharge test reports, because they need to perform these tests. And you should ask your colleagues manufacturing for you such transformers that they provide you with these test results. Okay? How these tests are being done, it's slightly different, because what's happening in the case of a distribution transformer and the bushings of a distribution transformer is that they do not have that capacitive coupling. So what is being used, it's usually a coupling capacitor, and this coupling capacitor has a preamplifier, and eventually the signal gets back into the ICM system that I discussed. But what's the takeaway here? Again, you have a test object, the distribution transformer. You find ways to receive the signals from this distribution transformer by means of such coupling capacitors, tuned with a certain voltage versus the either the high voltage, but generally it depends, generally to the high voltage side of the distribution transformer. And then you acquire that information, examine the partial discharge signatures, levels, and then you can say, okay, this was a well-manufactured transformer, well-repaired transformer, okay? Now, you can understand that everything I'm telling you now, and I'll show you towards the end of the talk, can also be determined online. So you can actually ask yourselves, being a power utility or a company that has such kind of transformers in their exploitation, okay, so nice, I got a good transformer one day from the factory. How does this transformer evolves during time? And basically, again, monitoring for partial discharge becomes a very interesting topic. Now, rotating machines, I mentioned to you, rotating machines are also subject to the same issue, right? So you have high voltage, you have partial discharge, and it's a good idea to look at, again, the quality of the rotating machine you have received, being that a big motor, being that a big generator, okay? These things also get repaired, so it's very important to carry out partial discharge testing. So naturally, what's happening during those times is that you will have the rotating machine, and of course, you would like to acquire the information from this. So you will use these coupling capacitors, in this case 14 kilovolt for a 6 kilovolt machine. You will use such kind of coupling capacitors that are going to draw the information out when the rotating machine is being powered. Of course, then the question is, how do you power this rotating machine? Because it can be powered when it's functioning, or being a generator, or you need to bring external power. I'll discuss that topic too. But fundamentally, again, it's the same concept. You have a test object, you have the sensors, and then the information is being drawn into a system that eventually will look at the signature of that particular test object, will look at the quality of that test object. That's how you should think, right? So I have a test object, I have norms that specify the levels of partial discharge. Possibly I have a new or a repaired. I need to know how well they repaired that thing for me, what's the quality when I got it. And then maybe it's a good idea to continue to test for partial discharge as time goes by, because then you are going to have, same as for a person, some blood analysis done at this time, another set done at this time, another set done later. So you can look at the trends, and those trends are going to give you a very important piece of information that will give you more or less the action that you need to take in terms of doing condition-based maintenance. Condition-based maintenance is not something that you are not encountering in your day-to-day life. Nowadays you are driving relatively modern cars. They will tell you when you need to change the oil based on how many kilometers, how you drove it, etc., right? This is condition-based maintenance, which in some way helps you save money. If you drive in a more, let's say, relaxed manner, and you don't drive so many kilometers, you will need to change your oil a bit later in your car's life. Well, same with such kind of assets. It depends how you are exploiting the asset. If you are taking it very close to its limits, of course, the life of that asset is going to deteriorate faster. So it will be very important to take such kind of data points from the moment when the asset has been produced or repaired all the way towards the end of that asset's life. And then you are going to know very well when you should be scheduling maintenance. Because, for instance, let's suppose that you are running a coal-fired plant, a CHP plant, and then you are going to do some maintenance on the coal burners. Well, it will be ideal to synchronize that with the maintenance on your generator. So by looking at what's happening with the generator, you are going to be able to make decisions when to do that maintenance. And these are the kind of important things that condition-based maintenance concepts are going to let you know, tell you. Of course, in some cases, there are cast resin transformers. And here I'm just showing, again, an example where the power supply, I'm only trying to show you this because I want to talk for a second about powering the test object. So in this case, for instance, you see another equipment from our company that is actually used this time not as a tester of the cast resin transformer, but it's used effectively as a power supply, clean, PD-free power supply. And then once you power the test object, which is the transformer, then you're going to carry out exactly the measurements that you saw in this particular setup. So powering the test object is another subject of our conversation, and that has to be done in a filtered manner, in a PD-free manner. So I'm going to now jump to a different set of issues, more about test and measurement using the ICM Flex. This is a uniphase type test that basically can be done with one equipment in a very easy way. I've used it myself. In fact, I've used all these pieces of equipment myself, and I'm telling you, this is one of the easiest thing to use because it's only a matter of doing a couple of connections. Here I try again to capture what's the application, right? It's everything from cable to rotating machines to cable joints. This is how you test those things. Of course, you have to power the test object again. Then why do you need to test? Because there are normatives, there are standards that explain how to do that. And of course, who's going to do it? So this is just a symbolic representation because I'm not here to market our products. You have to understand that. I'm here to discuss technically how these are being used. And so here, yes, you see it in action. You see the ICM Flex, you see the filter, you see the coupling capacitor, etc., to be used in comparison with another instrument. But what you see here, you see a reel of cable. So ultimately, the whole concept here is rather simple. You use a high voltage power supply, MEGGER, for instance, being one of the organizations that produces such, MEGGER being one of the organizations that produces such high voltage power supplies, but again, if they are PD-free, other manufacturers can be used. And then the voltage goes through a filter and then goes to the ICM Flex. This is a very nice unit because, as you can see, it's battery powered, talks Bluetooth, so you don't need to be near the test object. So you can have the test object safely at a distance, being cable, being rotating machine, and then you're able to, again, take the stethoscope out and get the information from a partial discharge point of view. And again, that will give you a signature that will tell you, is this cable good or not? Is the joint good or not? Remember, I listed here all these applications that you can perform with such an equipment. So here I'm also showing when somebody wants to use the same equipment to do rotating machine testing. So you can see one of our test vans that basically is used to host the equipment. We can have a step-up transformer here. We can have a power supply that basically is controlling is controlled in voltage, and this step-up transformer gives exactly the needed voltage for the single-phase testing of this particular motor in this case. So we will connect to the terminal box. You can see the flex, the filter, and the flex, and then more or less it's a push-button exercise to get the information, the partial discharge information based on those standards. Here you can see the same device used to check in fabrication stator bars. Here you can see the same device used for switchgear. Here you can see the same device for big motors used. Here you can see in the case of other motors. So you can see the simplicity of the setup and how it's being used to acquire the information. Of course, these signatures at the beginning, same as now you're learning more about a partial discharge, you will start learning about interpreting such kind of diagrams, and you will work hand in hand with people like us to tell you how to use your knowledge, your database of such kind of PRPD diagrams in order to enhance your knowledge and be able to interpret the diagrams yourselves. In this case, I'm showing you, for instance, another device, but not so much for the sake of showing you a device, but to tell you that another sort of very important test object, the GIS-GIL, can be also tested, measured, spot checked, and of course, naturally, can be also monitored. But in this case, I'm just talking about test and measurement preponderantly in the entire talk. So we have here the ability to look from two perspectives at the GIS, from a UHF perspective, and we have the opportunity to look from an acoustic perspective. Funny enough, the same instrument is used for both, so that's very efficient for you. And naturally, the people using this, commissioning, test engineers, people in the factory, based on the SIGRE guidelines. So if you look, you will see the system that can be basically either a desktop or built inside of an Explorer case. Again, very easy to be taken to the factory floor or in action because it has autonomy, battery, and everything else that is needed. And effectively, one can connect to the GIS in many, many ways. So I'm going to show you here a couple of ways. So when you have all the GISs, they do not have built-in antennas. So then you will have this spacer, epoxy spacer. So then you're going to use an external antenna to gather the UHF information. In other cases, you had a hatch window. We have specialized antennas that can be mounted on top of such kind of hatch windows. And tomorrow I will detail such kind of things a bit more. And then, of course, you can have built-in antennas. And the net result is that you can use such a device, a multi-purpose device, to acquire information either in a UHF sense from the GIS, or you can also use the device to acquire information acoustically. And you have to know the acoustic part usually is used to locate precisely where the fault happened. The UHF, it's more of a recurrent test kind of procedure. So when it's applied, it looks like this. So you will have several, on the GIS, several such acoustic sensors, and you are going to gather eventually the PRPD diagram. Naturally, you need a synchronization signal that will help you understand where things occurred on the phase and then after that you will be able to say exactly the location of the problem. Also, you will have maybe a PRPD representation of the problem, and the net result you're going to see in this case that you have a hopping particle that it's located in a certain area of this particular GIS. So the same device, as I mentioned, in this case in an Explorer case, can be used to look with hatch, with embedded antennas, and you can organize a maintenance program for your GIS with a relatively low-cost device and not too much effort that will require leaving this device a couple of minutes or a bit more to acquire patterns on a regular basis. Of course, this is just, I will say, the easy way instead of doing full monitoring, which will be probably the recommended path going forward. So here I'm showing the same thing done with these hatch antennas. There are other ways to connect here. Some of the manufacturers provide the ability to open that particular visiting window, dig this special substance that is really some special silicone, and connect to a sensor that is built in. So there are many ways to deal with the GIS. Yesterday I had the pleasure to discuss with colleagues from ABB, and yes, we concluded that this is a very nice way to go forward and have such kind of opportunities of testing, especially when they go in the field, especially when they start blending different parts of a GIS even with other manufacturers. And yes, one unit like this can help. In this case, I'm showing the same thing with other types of placements of the acoustic sensors. So maybe a takeaway message here that has a bit of a marketing flavor is that our company, being in this business since 1990s, we have gone through all the hoops necessary to actually work with both manufacturers and utilities, and we responded to their needs. So most likely, if you have a problem, come forward to us, come forward with GAE, and they will provide you with a solution, because most likely that solution exists already. It's just enough for you to speak up about your problem. Here I'm showing another device that is used. This is a single channel device for everything in manufacturing to a large extent, from cable testing to instrument transformer and even microchip testing, because as you know, for instance, in these modern meters, you have a microchip that works both on the high voltage side and also on the low voltage, the measurement side. So these kind of chips, again, need to be also tested. And maybe here I can tell you a little story. Do you know that for partial discharge to be triggered, to have those electrons jumping, sometimes you need random cosmic waves, and of course waiting for that is not necessarily an option in production. So you basically can also trigger that by using X-rays. So our company will manufacture such kind of test chambers that are using the device I'm talking here for acquiring PD information, are using other devices to actually power, and also the X-ray unit in order to trigger partial discharge. So again, in this case, an example that resembles a bit what I showed you with a transformer initially, but it's just a one channel situation here. So you will have a sample. The sample basically needs to be, again, powered at a certain voltage. How do you do that? You do that through a PD-free step-up transformer. You will be able to calibrate, naturally, the test circuit. You will have a coupling capacitor reading signals from the test object, and eventually you will have this ICM compact. Here at the bottom you can see the voltage controller that we built in order to manipulate the voltage and in fact automate the test procedure. So colleagues from different companies, from GIS to chip manufacturers, from transformers to actually switchgear, medium voltage switchgear, they use such kind of setups. Our company sells to many people, so. In that case, I'm just showing you how the ICM compact is being used. we are powering the device. And yeah, these are typical examples that you can see for cable, for transformers. So ultimately, these devices can do everything that you need in order to do partial discharge testing. So, because I talked a lot about test and measurement, I just want to touch upon the concept of monitoring and tell you that it's not enough to just do test and measurement. You can organize a maintenance program, a sort of a round robin, but if you have a bit more money, and if you are very concerned about the state of your assets, maybe you can go one step forward in the direction of monitoring. And of course, I know many utilities that have done that. I know many customers that have done that. And here I'm going to show you just how we do with the ICM monitor and GIS monitor the monitoring of such assets, just to put an end to my presentation. So in this case, you can see a rotating machine. You can see the coupling capacitors. All this can be mounted very nicely to a connection box. And this is the moment when you can have one initial decision to go for temporary testing. You can use one of our devices to go into a round-robin fashion from one device to another, from one test object to another. Or at one point when you see that you have a problematic test object, you can permanently connect to that a monitor. And it will look like this. This is an example I installed, for instance, for a big American company in Bulgaria that they are processing corn. And these gases from corn processing into sugar are used actually to burn in 2 CHP turbines and effectively generate power. So naturally the generators ended up being monitored, and you can see here on this, you can see the generator, you can see the coupling capacitors, you can see the connection boxes, and eventually you can see in this case represented generically a monitor. Naturally we manufactured that. So this is how these monitors look like. We are also using them for transformers, and many colleagues here that are even exhibiting next door, General Electric, Maschinen Rheinhausen, naturally Siemens Konchar, they are buying from us such monitors, installing them all around the world on assets where people honestly care about their livelihood. Here I'm showing also how it's done for a variety of other distribution transformers. You will say, why monitor such a distribution transformer? And I'll say, again, it depends very much what is this distribution transformer powering. Is that important mall? Is the president's house? Is the military air base? You tell me, you decide if a distribution transformer deserves the, let's say, monitoring that some people are using. In this case, I'm showing you, of course, one of the flagship systems that we produce. We can have it up to 500 channels. I'll discuss this more tomorrow, so I will not insist too much, but this is a bit of an appetizer for tomorrow, everything around the concept of GIS, GIL monitoring, which is a big topic these days, especially in countries that have implemented GIS, GIL systems, and I think you are one of those countries. Here I'm also showing what we do for cables. It's basically the same type system that, in this case, with coupling capacitors, HFCTs, or built into the joint coupling capacitors, help us acquire the UHF information, help us do a monitoring. This is an example actually from the Berlin tunnel. So overall, this is really my conclusion slide. You can have a service company or a manufacturing company, or you can have a test company, you can have a power utility, ultimately operating in one of these industries that you can use some of these systems in order to perform the tests that I just showed you. So I think I can stop here, because I think it will be very nice to have a bit of interaction and maybe hear from you some of your concerns, some of your questions. So thank you, and I'll let you step up and ask some of the interesting questions.
Thank you, Mr. Mihai. Mungkin dari hadirin sekalian, jika ada pertanyaan, untuk pertanyaan tidak usah ragu untuk bertanya dari dalam bahasa Indonesia. Nanti akan dibantu oleh tim dari GAE. Juga mungkin bisa dibantu oleh Panito ya Pak, untuk pertanyaan dalam bahasa Indonesia, atau dari Pak Pet juga bisa. Monggo, dari hadirin sekalian, jika ada pertanyaan, silakan. Mic-nya.
Thank you, Mr. My name Yudhistia. I am from Semen Padang. In my company, I have a PD locator maybe, because the measurement use dB, not picocoulomb. My question is, what correlation about dB and picocoulomb?
So, as I mentioned to you, when you have a charge that's measured in picocoulomb, this impulse generates UHF. When you measure UHF, you measure in dB microvolt or in dBm. There is a relationship. For instance, if you have a 50 ohm impedance, dB microvolts is, I think, 107 minus dBm. But ultimately, when you measure UHF, you measure in dBm or dB microvolt. When you measure the movement of these electrons up to 1 megahertz based on the IEC 60270, you measure in picocoulomb. For instance, you will never measure in picocoulomb in the case of a GIS system. There you measure in that dB microvolt. But in the case of a transformer, where you have those bushing adapters, or you have the dolphins and the quadruples, you are going to measure in picocoulomb.
So it's mean my measurement is indicate PD activator. We usually measurement in switchgear.
Yes.
So it's mean indicate the PD activator is my switchgear.
Yes. So what you're measuring, it's, let's say, same as putting a voltmeter and looking how many, let's say, dB microvolts you have.
Yeah.
This, I will say, this is the first step. The next step is to get to the PRPD diagram to say what's the problem. So if you just want to, let's say, use, we manufactured those too in MEGGER, a handheld scanner to say I have PD inside of this cabinet, I would say this is just the first step of a bigger diagnosis. But when you have a big asset, expensive asset, like a transformer, like a GIS, you want to go maybe 2 steps forward. You want to go, one step is to actually understand the type of fault you have and then localize it. So let's say in the case of a transformer, you just take that winding out and send it to the factory, not the entire, how many tons transformer. Or in the case of a GIS, you're not going to disassemble the entire GIS, you're just going to look at a certain section. So finding that you have in a certain area of your cabinet PD, great, one first step. But taking those other steps, I would say, especially for expensive, high voltage assets, are very important too.
It means the first step I have done, and for the analyze, we need 2 steps again.
Yeah, same in the case of your car. So you have the yellow check engine, and now you need to put a computer to find out, is it a problem with the injectors or is it a problem with the turbine?
My second question is,
Please.
if we already know there is a PD there, can the PD reduce, or we monitoring until it's failure, or it can be reduced?
It depends very much on your asset. I'll give you examples. Certain assets like GIS, GIL should not have any PD. Motors or generators, by definition, have a certain level of PD. So you need to understand very well the asset you're dealing with. Okay?
Yes.
For instance, in the case of a transformer, in the factory, you have 200 picocoulomb as 250 as a limit. Now, when you go with the same transformer in the field, the picocoulomb level, it's obviously higher because you're going to have disturbances from corona, from other things. So you need to understand the asset. you need to understand the test environment where you're testing. And after that, you can make decisions what, first of all, to do further. If you want to localize, if you want to treat that asset, if you are accepting certain levels of PD or not.
Okay, thank you, sir.
Thank you. Good questions. Gave me an opportunity to explain a bit more. Thank you.
Baik, terima kasih Pak. Ada lagi pertanyaan dari teman-teman lainnya?
I can offer mine. It's working.
Hello, my name is Irfan. I'm from PT Guna Elektro. I am involved in switchgear business. We have manufacturing in our shop. My question is, when we test the switchgear using PD, and we get all information from after testing the curve or pico column or DB whatever, the most important thing is we have to give recommendation to our client. For instance, we have the job in on site, the all switchgear, we test using PD or whatever, yeah. The most important thing after we test, we should give a recommendation. The first question is, do you have any reference standard or IEEE or IEC or whatever about partial discharge in switchgear?
For what I know, for switchgear, there are guidelines. You can look at some secret guidelines. I don't know exactly what equipment you're using. We, for instance, sell ICM compacts to colleagues from Phoenix. Actually, funny enough, our competitor now, because they were purchased by Doble. But what I'm trying to say is that inside of their manual, you also have, and they produce such exact, I've been to Canada where I helped them set up some things, and inside of the manual, there are also guidelines for, in particular, switchgear.
Maybe you can share later to us.
Yes,
all information, because the important thing, if we investing that equipment, we do some servicing at site. It has many brand. It can be GE or whatever. We have
doesn't matter. Yes.
To test, and finally we have to give them recommendation. For instance, this is exactly should be maintained as soon as possible, or replace the part or whatever. Thank you.
I understand your concern, but be careful here, because the guidelines that you're going to get are guidelines in, let's say, a quiet Faraday cage special test room. When you go in the field, like I mentioned for power transformers, first of all, there are no real numbers there. You have to develop your own sense, because it's very important, the environment. If that environment is full of corona and so on, when you're going to do partial discharge testing, you're going to see very high values. So you need to, let's say, use a unit that, let's say, has a gating capability, and you need to know how to use gating in order to suppress such kind of disturbances and be focused on the asset. And this is, that's why it's a bit tricky here, because you need to understand yourselves, first of all, the use of the equipment, subject number one. Subject number two, what's the environment in which you are testing? I was recently actually in this factory in Quebec, in Canada, and they had some big problems because it was an ABB factory next door, you know, the split Hitachi ABB. I was in the Hitachi side, but next door they were developing robots. And these robots had basically switching power supplies, and whenever they were playing around with the robots, plus with the crane next door, they were inducing basically partial discharge. So they needed to be very careful when they performed the measurements. And this was actually in a let's say, controlled environment. Now, imagine the same thing outdoor when the guy next door starts welding. That's the end of the test. You need to be very careful what kind of disturbances you have in that environment, wherever the testing takes place.
Okay, next question, sorry. Yeah. Other option is it possible also if we test and send all information to your company and get the feedback?
Yeah, I mean, naturally, if you have used our devices, and if we talk, especially because we have this special partnership, we will be able to help you to understand more. Our intent is twofold. Of course, to sell some devices, but also to educate the market. So working with somebody like you together to understand better where, what you're testing and what conditions, and for you to understand that and be able to service your customers, it's probably in long term in our interest, because then more people will understand the benefits of performing such kind of partial discharge testing. As you've seen from the hands that were put up at the beginning of my talk, not so many people are yet familiar with the benefits of testing for partial discharge.
Yeah.
Many people, to be honest with you, consider this voodoo, black magic, and so we need to we need to demystify this domain.
Okay, thank you.
So I'll be delighted to find ways to collaborate
Okay, thank
between
you.
our
Thank you.
organizations. Thank you.
Baik, terima kasih Pak. Thank you Mr. Mihai. Maybe for the session.
One more question at the back.
One more question. Okay, one more question. Dan terakhir untuk sesi ini supaya bisa lanjut ke sesi berikutnya.
Thank you, Mr. I want to ask about the PDX. I don't know if I missed or no. The question is, how much the influence about the noise with the testing acoustic your PDX? And the second question is, there is a limit about your noise, about your PDX acoustic
Okay.
testing?
So our equipment,
Thank
of
you.
course, will acquire noise, right? And there are many ways to deal with noise. One has been recently mentioned in the context of gating. Another one is to raise the noise floor on our devices, and therefore that noise will not be considered when you look at a diagram. Now, you also have to characterize that noise. If that noise, for instance, has a corona kind of, let's say, source, you will see it in the partial discharge diagrams. The only problem now is, do we see this corona covering? So in other words, if we have very powerful corona, do we see that covering the real partial discharge problem inside of that asset? And this is the place where you need to have a specific measurement done. You need to understand the conditions, and then you need to understand what can you do to suppress that corona. Nobody can do, same with doing, let's say, radar sweeps. If you have a sea of noise, let's call it electronic noise, you will not see the target because it's covered by noise. So now the question is, how do you suppress that noise? And usually there are either environmental ways to do it, or what I mentioned to you, gating, or raising the noise floor. But if the test object exhibits certain partial discharge issues, and that sank in the sea of noise, no person on earth will be able to help you with that. So that's why, for instance, some of these tests are done in special test rooms, Faraday cages, especially in production, because people want to not be subjected to this noise. Yes, but once you go in the field, that's the place where it's very important to understand where you're going to place sensors. Sometimes, where do you place gating sensors? Because we have special corona suppression antennas, we have high frequency current transformers that you put on the ground plane. So you need to use those many times to suppress noise, to gate noise. Those are the methodologies usually used. Yes.
Thank you.
Thank you. Great questions. Each one of them gave me a chance to tell you a bit more. So I really appreciate that, and I really appreciate the audience here. So thank you for the opportunity. Maybe I have a chance tomorrow to tell you more about GIS, GIL.
Thank you,
Thank you.
Mr. Mihai.